All right, we are live. Happy Friday. So, this is the end of week 3 already. That's crazy. This quarter is like going by really fast. Um, that's all right. All right. I will talk about the ODP in a minute, and I'll go through some sample code for that. But any questions up front? Anything you want to go over? All right. Well, let's just take a look at ODP 205. So quick reminder, right? Struct node, data, and next fields, and you're writing a function called set, which does something kind of peculiar to a node. It doubles the data value, and it sets the next field to null. There's no good reason to do that, right? But it's just what the ODP asked you for. So it can be as short as 2 lines of code, right? You have to define your struct node. I didn't need standard io.h in here, but it doesn't hurt. Oh, I guess I needed that for null. Okay, so I did need that. But there's the definition of the node. Here's the function set. It doesn't return anything, so it's declared as a type void. But it takes one argument. You can call this whatever you want, but it's got to be a pointer to a struct node. And then, in arrow data says take in, which is a pointer. The arrow says use the thing that it's pointing to, which is a node, and look at the data field. So this is the current data value of that node, multiply by 2, and then save that where? Right back in the data field. And then for the next field, we're not modifying, we're just setting, so set that equal to null. So yes, you are using null from here on out. You're never going to use my null again. So null is the official safe to use memory address pointer in C. Yeah, we'll have a goodbye my null party on someday. Let me make a note here. So I tend to write these things as a star next to a next, saying that next is a pointer to a struct node. But, some people prefer to write it like this. It's exactly the same to the C compiler. It really doesn't care about the spacing. If you don't have a space, I think it'll get upset. But like this, it looks like next is a variable. What kind of variable is it? It's a pointer to a struct node. And if that makes more sense to you, feel free to write it like that. I'll usually write it like this, though, which is saying, it's a pointer just like integer star I. But either way is fine. I have a hard time when I start 222 remembering if it's uppercase or lowercase null, because Java makes it lowercase, which always feels a little strange to me. But on the other hand, bold-facing something that's supposed to be nothing, or uppercasing something that's supposed to be nothing, seems a little contradictory. But yeah, it's uppercase null. And if you like lowercase null, you can define it. Pound define lowercase null to uppercase, but don't do that for other courses or on the job. All right, so this will do what the set function was supposed to do, and it's kind of a prototype of how we're going to do all of our interactions with structures. We're almost always going to have pointers to structures, right, as opposed to just bare structures. And when we have a pointer to something that has multiple fields to it, this is the easiest way to dereference that pointer, right? Name of the pointer, arrow, name of the field. and that does the, you know, star in dot data in this case. Alright, I was going to post more ODPs today, but I decided not to because then you have to work on it on Friday. So I'll start with some more ODPs on Monday morning. That'll be related to PA2, and it'll be similar to what we did with PA1, just sort of building up different parts and pieces of the programming assignment. So the pseudocode for PA2 is really no different from PA1 for most of what we're doing. The add, search, delete functions are exactly the same algorithms, right? So let's just quickly run through the pseudocode for add once more in case you didn't nail it on PA1 or you've forgotten it because it was a week ago. And then we'll talk about freeing memory and how that ties into leaks, because that's the one new algorithm that we have to do. And if you were getting a leak after doing add, yeah, it's probably because you didn't free the memory at the end of the program, and that's a special extra step that we have just for PA2. So we'll talk about that next. But let's just quickly review linked list manipulation. So we want to insert a number, right? So add some number n. And we always need a sentinel node, right? So, oh, I'm getting laggy, man. Hold on a sec, let me see if I can tweak that. I've decided it's Zoom that's killing my performance, by the way, because I can run both cameras and I can run the screen recorder and everything else, and it works great. And then as soon as I turn on Zoom, my fans start spinning out of control, and so I think that's an issue. Let me try. Let me try a different output format. Oh boy, I just killed it. Alright, technical issues, hold on. Alright, enough of that. Yeah, Zoom for Linux does not get updated as frequently, which was why I got into this whole bizarre setup, because Zoom lets you share a portion of your screen, but under Linux that feature didn't seem to work even a few months ago. Now my camera here is a low res thing. My document camera is high res, and that seems to be why it's laggy. But it's working right now, so we'll see if that works. If not, we'll just deal with it. I'll put some syncopated jazz in the background or something. All right, so let's just review the add algorithm. So we want to add a number n. We always have to have a sentinel node. So the arguments to this might be, you know, sentinel and n. And we have a pair of pointers, so I'm still going to call them current and previous. All right, and first thing I'm going to do is create a new node. So how do we do that? We call malloc. Right? If you want to put your malloc inside a getNode function, you can do that and have getNode return a pointer to a struct node, and then, you know, inside getNode call your malloc. But if you want to call malloc directly from inside add, that's totally okay with me too. Create a new node, and then start off with a pair of pointers. And again, I would make previous the sentinel node and current the thing after the sentinel node, which could be null. That's okay. But we know this sentinel always exists, so previous will not be null. Current could be null. And so we can do the same while loop while current is not null. Well, if we get inside the body of this while loop, this is an existent node. And so see if current data is bigger than n, then we want to insert right before current. And so set new next to be current, set previous next to be new. And that sets up your pointers like this. And then return. Otherwise, if this node is smaller than the one you're trying to insert, move down one spot. So move along. So set previous equal to current, set current equal to current next. And go back and try it again. So that'll change this to be previous and this to be current, and we'll check this node, and if that's not the right spot, we'll change previous to be here and current to be here. And maybe this is the first number bigger than n, so we want to insert right before here. Right? So in that case, we would change previous to point to our new node and new to point to the current node, and we've sandwiched it in between the right spot. And then if you fall out of the loop, what does that mean? It means you got to a case where this was the last node. This would be previous, this would be current. We didn't want to insert before that last node, so we moved our pointers, and now current is null. And that kicked us out of the loop. Well, so all we want to do is add our new node after the node that we're calling previous. So previous next equals new, and new next equals null. And this is just adding to the end of the list. And if you can do the add, you can do delete, you can certainly do search, and you can definitely do print. Add's the hardest because you have to keep a pair of pointers and you have to go back and adjust pointers to include this new node. If you want to delete, right, you do the same thing. You move through with a previous current pair. When you find that you want to delete current, then you just change previous next to be whatever current next is. And if you're deleting the last node, current next will be null, so your code will be setting previous next to be null, which makes that the end of the list. And if you're deleting the first node, previous is a sentinel, so you would be setting the sentinels next to point to whatever the first node was pointing to. So that works in all cases. Alright, which brings us to the last detail, which is freeing memory at the end of your program. So your program can work perfectly fine. You can free memory when you delete it at the same point that you called release node. But to free the memory at the end, we need to do something that we didn't have to do in PA1. Because PA1, we just had a statically allocated array, and the system will reclaim that space when our program exits. PA2, all of our nodes are allocated at runtime. They're dynamically allocated. So at the end of the run, I suggest you make a function called something like, free all, or release all of the memory, or restore all allocated memory to the dynamic memory pool so I don't lose points, or whatever you want to call it, right? But some function that you call to basically release all of the nodes that you've allocated. Is null slightly more complicated than just 0 because I was playing and I couldn't assign it to... Yeah, null is different from 0. Null is actually a pointer to void, and it has a value of 0. But on a 64-bit system, null is actually an 8-byte value. It's a 64-bit version of 0, whereas an integer 0 would just be 0, and you'd have to cast it to a pointer. So if you use NULL, it keeps you out of trouble. Alright, so at the end of your run, you want to call something that frees all of your nodes. The algorithm for this is not too bad, but it's a little subtle. So here's our sentinel. There's our linked list. Here's one suggestion. There's simpler ways you can do this, but since we're already using a pair of pointers for delete and for add, you can use a pair of pointers to clean up your list. Set your previous node to start at the sentinel. Set your current to be the thing the sentinel points to, and the idea is we're going to go through a loop and we're going to continuously free previous. Alright, we're going to free previous, and then we're going to set previous equal to current and current equal to current next. So here's the visual picture, and then we'll do some pseudocode. I'm going to imagine that I'm currently examining this node. Okay, my current node. Once I have, something pointing to this, I'm going to free previous. I'm going to return that to the memory pool. I'm just going to call free previous. And so this node is gone. I can't use any of the fields here. I don't need any of the fields here, though. I don't need this thing's next field because I have this variable current pointing to this node. And that's all I need to say, okay, set previous equal to current, set current equal to current next. And now I'm going to say free previous, and this is going to go away. And when I free this, previous is still pointing to this block of memory, but I don't know what's in that block of memory anymore. It's potentially been, consumed by some other process already. But I don't need to use that block. I'm going to say previous equals current, current equals current dot next. I'm going to free previous. And I'm going to keep doing that until I get to this last node. I'm going to free previous. I'm going to say current equals previous equals current. I'm going to say current equals current next. So current is going to be null. And at that point, I'm going to kick out of my loop, but I still need to do one more free. I still need to free this last previous. And then I'm good to return. And the reason this is a little easier with 2 pointers instead of just one is that we can't, once we free this node, we can't use any fields from it. Right? So if we just have one pointer and this is current, we can't free current and then use current next to find the next node. Once we free this, we're not allowed to touch it. And valgrind will throw warnings if you try to do that, I believe. Alright, so how do we do this? So previous equals the sentinel, current equals what the sentinel points to. Free the previous node. And just keep doing this. So we're kind of standing on the rock labeled current. We pick up the rock behind us and toss it back into the water, right? So that frees that. And then we move to the next rock, right? We change our position to the next node, but before we do that, we remember what the stone is that we're standing on right now, right? So we save that in previous. Then we go back up, we pick up the previous node, we toss it back in the pool. So we do all of this while the current node is not null. When current is null, it means that previous is equal to the last node in our list, and so when we come out of here, just do one more free the previous node. Okay, that's a way to do this that I think is fairly straightforward. You can play around with other approaches, right? It might be reasonable to do while previous is not null, right? And then when we do this last step and we say current equals null, right? Previous would not be null, so we would go through this loop again and we would free the previous node, which is correct, and we would set previous to current, which is also correct because now previous will be null. But when we do current equals current next, we're going to segfault because current is null. So I think it's cleanest, at least to me, it's most obvious to still iterate, while current is not null, to know that we've processed the last node. But just remember, when we're processing a node, we're releasing the previous node, and so we need this extra free statement at the end. So play around with that, right? If you don't free the last node, you'll get a memory leak. If you free too many nodes, you'll get a segfault. So it will make it pretty clear if you're doing the right thing or not, if you run this through valgrind. All right, questions on that? Yeah, you do have to find the Goldilocks zone for node freeing, or for any of this stuff really, right? Same thing with traversing or deleting or something like that. There's always this tension between not including the last node or trying to include too many things. Same thing with parsing arguments, right? You go less than argc, less than argc minus 1, less than or equal to argc, right? There's a sweet spot somewhere in there. So yeah, that applies to a lot of what we do. Alright, so I want to play around with some things that we can do wrong and see what happens with valgrind when we do this. So let's make a sentinel node, right? So I'll call malloc with the proper size of argument, right? The number of bytes for a struct node. And then let's print out what the value of that sentinel is. I'll print it as a %p, so we should get an address. And let's look at what the data value is to begin with. Alright, so, oh, that's my shortcut. So when I run v, my sentinel value is, you know, some interesting looking memory address, and the initial data value is 0. Right? So that looks reasonable. If I run this in valgrind, I get a couple of things. First of all, I get a leak, right? Because I allocated a sentinel node and I didn't free it. So let's go back and free that. Alright, so it still runs. If I valgrind this, my blocks were freed. There's no leaks possible, but I've got warnings. Right? I've got all of these messages up here in the beginning, right? So you gotta get rid of all of those to get points for not having leaks or memory issues. Alright? And it pretty much tells you what's going on here, right? It's telling me inside main I'm calling printf, right? And I've got something that depends on uninitialized values. Now it won't pin down a line number in main. It tells me it's line 33 of printf.c if you want to look at the source code for that. But it's an uninitialized value, right? What's the problem here? Let's compile with GDB on and run valgrind, and now it's telling me this is a problem coming from line 16 of my file v.c. So let's come in here and go to line 16, and it's this print statement. And what I'm using in here is this data field of the thing sentinel points to, and valgrind is warning me that I have not initialized that, which I haven't, right? I'm trying to use a data value before giving it a value to use. And that's not something you want to do. That's like saying integer I, and then saying if I is equal to such and such, do this thing. Well, if you haven't initialized I, you have no idea what that code is going to do. It depends on what random value I happens to have when your program is running. So it's keeping you safe, right? And it may be that, you know, when we malloc, we always get a 0 in the data field. Maybe that's what we were expecting, and so our code works great. But it's an issue. And it's something that, you know, this code might work perfectly. I might not be able to make it crash. It might run great on here. And then you port it to a different system. You run it on a Raspberry Pi, for example, and it's just like totally buggy. And it's crashing, and it's giving weird numbers and things like that. And it's because you were unintentionally using this idea that on one machine, you know, allocating memory always gave you things that were initialized to 0. So seriously pay attention to these. Right, so I don't know why I'm printing the value, but you know, if somewhere this thing had been given a value, right, then when you run it, you get this nice clean output. So no warnings, no weird issues. There's the output from my program, and then the heap summary. All blocks are freed, no leaks possible. If you try to free something twice, you get a problem. Pretty cryptic message, right? Free, double free detected. Right? So it's telling you you're trying to free something that's already been freed. And so your program aborts and it dumps the core. And if you run this in valgrind, it will tell you invalid free, and it's right here down at line 21. And it tells you this is a block of size 16 that was freed at line 20 and allocated at line 12. So this is giving you a ton of information, right? You got a block allocated at 12, freed at 20, and then tried to free again. I don't know how to turn on line numbers, but you know, here's line 12, here's line 20, and here's line 21. So yeah, if you read the description for PA2 and you read the grading rubric, all memory has to be freed when your program exits. And you can't free it too soon, right? If you've got a linked list that you've built up, and you know you've got data stored in nodes that are pointing to nodes, you can't just free those, you know, just because it's convenient to free them right then. It's actually got your list. You've got that memory allocated for a reason. But when you're all done, right, you need to do this special one-time operation to just release all the nodes. So make yourself a function that that does something like that, and that'll free it. Hey, you're right, thanks. Alright, colon set number turns on your line numbering. Alright, so use valgrind, right? Use it as you're developing. It's much easier to find this problem in a small piece of code than in a big piece of code. So yeah, if the user inputs X before you exit, you can just call your release all nodes function, free willy or whatever you want to call it. All right, other questions on that? If the user controls C's, you can't really do anything about that. I mean, you can trap it, but I don't need you to do that. If you control C, that's a good question, though. I think valgrind will still... Yeah, valgrind will still kick in, but you're not responsible for freeing memory if the user interrupts the program. But that can be a cool way to see what's going on. And look at all this nesting, man. These are things calling things, calling things. We're in fgets, which called io_getLine, which called io_getLine info, and underflow, and ultimately called, guess what, our favorite function, read. Chapter 2, low-level system input function. And then we got a sigint, that's what Control-C generates. And then valgrind dutifully did its summary anyway at the end. Now you can trap Control-C's. You can use the signal call to set up a handler. And you could say when you detect a SIGINT, I want you to go ahead and run this function. You can make something that controls C, you know, causes a function to execute, and that could be your function that frees your memory, and so on. But I don't recommend doing that for the code you turn in, because if you end up, you know, with an infinite loop or something, and I have to control C, and you've trapped control C, it's going to bum me out. Because then I'm going to have to go to another terminal and kill it with a 9 and all that stuff. But you can do that, right? It's fun to play with. Make unkillable programs. But remember, you can always kill with a signal 9. That's untrappable, but most other signals you can interrupt or intercept. All right, more questions. Yeah, I wouldn't like freak out. I would just like kind of be bummed. All right. So that's everything you need for PA2, right? I mean, if you're mostly on top of PA1, you've got all the mechanics that you need to do PA2. Different node structure, same algorithm for this, slightly different init function, call malloc inside, right, and return the value from that. Check for null instead of my null. Use null instead of my null when you want to mark the end of a list, which you only really have to do in your sentinel node, because that null basically gets propagated to the end of the list when you do adds or deletes. Your main program, pretty much no changes, except your exit function has to call your, you know, release all memory function, and that's pretty much it. So I'm hoping that people make quick work out of this. I'm hoping that you get this coded and you know, have it running pretty well in final form in a day or two, right? And then you can spend some time kind of like, you know, marveling at it if you want, and putting some polish on it, and tinkering with it and things like that. It's not a good feeling to be trying to understand this stuff, you know, in the 11th hour, when you've got deadlines and I still got to push it on Git, and I got to add comments, and I got to, you know, make sure all this other stuff. So if you get it done earlier, that makes things easier. You could globally substitute my null to null, but I would say don't do that. You probably don't have my null that many places, and if you just make sure you get rid of the define, if you forget to change one, the compiler will tell you. But I think it's more useful for the sake of learning this stuff to, you know, actually type in NULL where you want it and really kind of think about what that's doing there, right? It's sort of forcing you to read your code and you know, rewrite it without necessarily typing it all in or starting from scratch. But it's up to you. Whatever you feel is you know, helping you understand this the best, go ahead and do that. But if you do too much kind of global substitution, it may, you know, end up feeling like one of these programs where you hope it works and it compiles and that's good, and it almost works, so I'm going to try to just fix up the last few cases that are giving me trouble, and then you're back to the realm where you've got bugs, and instead of getting rid of them, you're adding more stuff to patch them. So yeah, so, you know, whatever makes sense for you, it's a learning process, and it'll be different for everyone. Or you could define my null to null, but don't do that. I want to see NULL in your code. And if you take a course, you know, at a university, or you're on the job and you define my null to null, because you've never used null directly, right? It's gonna look weird, but it'll work. That's fine. And you'll find spots in standard I/O and other libraries where actually there's other things that are defined to be the same as null for different reasons. So that's not an awful idea, but do null anyway. And again, if you want, you can develop this in pieces, right? you can make a main program like we made earlier in the week that, you know, just cobbles together a list with a few nodes and work on your print function. Make this node and just make a sentinel node that, you know, points to a few data nodes, and then just call your print function with the address of that node. And once your add function is working, you could go ahead and do search. Search is pretty straightforward. It's like print, but you don't show anything. And you compare the data that you would print to a value. And then try add or delete. All right, any other questions? Well, we've got about 5 minutes left. Let me hop onto Canvas. So there's a quiz on Canvas that will help you play around with GDB. Let me take a look at that. Let me do a student view. So there's quizzes that are due at various points. So quiz 2 is coming up. Let's take a look at that one too. All right, so quiz 2 is mostly background, right? An integer array named x, right? What does x actually represent? Y equals star x, what does that mean if y is an integer and x is a pointer to an integer? A structure statement, and how do we set the field x equal to 0? These are things that, you know, you've already used these in code, right? And so these should be pretty straightforward, but you know, it might take some refreshing. Here's a question on the arrow. So which of these is equivalent to var arrow y? And this one can be a little trickier. Which one of these is likely to cause a seg fault? And you could try them, but think about them, right? And we're working here with the idea of uninitialized values and the idea that 0 is not a valid memory location. So that quiz should be doable, and that's due. I mean, you got a whole week to do it, but you know, that should be doable. So there's a GDB quiz that's due in a little over a week. That's in February. But take this one sooner than later. This will help you get up to speed more on GDB if you're not there already. For these, there's a file on the Linux server under /temp called G1. Difference between the arrow and the dot. Okay, fair question. So variable dot field. This assumes that your variable is a structure and that field is the name of, you know, an element in that structure. That's what we do in 121. Variable arrow field means variable is a pointer to a structure. So take the thing it points to and give me the field with this name. So this is just pulling a field off of a structure. This is pulling a field off of a structure that's pointed to by this variable. So it's dereferencing this pointer, seeing what it points to, and then grabbing the field. So it's just a shortcut for that. All right, so run GDB on /temp/G1. Start the debugger with start, and then this is basically a little bit of a lab to work through some operations in GDB. So set a watch point on I, and continue until I changes. When I changes value, it will tell you the old value and the new value. And if you want to continue running, just say continue, and it'll run until the next change. So do this until I is equal to 5, and at that point find the value of x. And you can do that by printing and put in your answer for x, and it's got to be a decimal answer. How many bytes are allocated for the structure called mystruct? So you're going to have to play around with this. You don't have the source code. So you set a watch point by saying watch space the name of the variable. So watch space I tells it to stop when it sees I change value. So we can say break space and put in the name of a function or a line number. We can say watch space and put in the name of a variable. How many bytes allocated for the structure mystruct? Play around with size of command. That's probably a good start. What is the address of the variable named data? And it will tell you some things about data if you just say print data. But we want to know that's weirdly worded. I'll go back and look at that. What's the address of element 0 of data? Data is an array, right? So when you say myFundData, right, data is pointing to a collection of, some sort of variable, right? But it's the address of the beginning of that array. So when you do this, what's the address that's passed to the function? What's the address of data 0? Well, in GDB, you can say print data. You can say print data bracket 0. You can say print ampersand data and see the address. You can say print ampersand data bracket 0 and see the address of that. So all these things that you could do in C while you're writing your code before you compile it, you can do at runtime in GDB, right? So you want to hop in there and basically play around with GDB commands, mostly prints, and answer these questions. What's the address of data 0, 1, and 9? What would be the address of data bracket I? Figure out a formula based on what you discovered in the previous questions. And then the mystruct, that's a typo, the mystruct field contains these different fields. Figure out how those are organized in memory. Alright, we're out of time. We'll go through more of this on Monday. But you can definitely do that quiz 2, which is due first. And we'll talk about these last few questions on Monday. Alright, I will see you next time. Take care. Bye.